Hi, I'm Ben-Yaakov. This presentation is entitled An Intuitive Explanation of the Multiphase Buck Trans-Inductor Voltage Regulator, also known as TLVR. Now there are two videos related to this presentation, one on leakage and one on multiphase PWM converters. I'm going to print the links in the description section of the YouTube video that you are now watching. I'm showing here a buck converter, which I'm assuming is used for a server in which we have a high voltage, say 12 volt, and there is a need to get a 1 volt, 1.2 volt at the output. So if this would have been one stage, and then if we have a load, which would be like a heavy microprocessor, and then we have a inrush current, that is the processor was hibernating and then it starts running. There might be a step here of the load of very high current, could be a few tenths of an amp, depending on the system. Now the output section here, of course, has a output capacitor, which has an ECL, equivalent series inductor, and then ESR, equivalent series resistor. And as a result, as we have this step here, we're going to have a dip in the voltage here. First of all, because of the drop of the ESR, also due to the ESL dIdt, and then we're going to start discharging the capacitor, and therefore we're going to have this dip here. Now in a system, of course, we're going to have a closed loop, a feedback, and this will initiate a change in the control, say a signals coming here to the gate, and once they are arriving here, then of course the inductor current will start rising. Okay, the maximum will be when this will be clamped to the input, and we have the maximum voltage across the inductor. So the inductor is rising, and of course the IDT here is very, very important. It has to do with the size of the inductor, of course, and if it is one stage, usually the IDT will be too slow, and this will be insufficient to keep the voltage from dropping to a level which is harmful, and we are talking about, say, 10 millivolt, 20 millivolt, fairly low voltage. Now, one way to approach this would be to use a multiphase, say, buck converter. In this case, we have a number of stages here, a number of half bridges. Here are the inductors. They are all funneled here to the output. Normally, we're going to operate them in an interleaved manner. That is, they are not operated together, but phase shifted within the period. And here, I'm showing the comparison of, say, one single inductor, and this will be the ripple here. This one is the ripple, which is fairly high in this particular case, like 80 amp. And the green is the actually gate drive in this case. Now here I'm showing the drives for the multiphase interleaved. We see that the pulses are shifted like this, and as a result the current of the inductors are also shifted, and we see here the interleaving, and as a result the output ripple will be low because there is a partial cancellation of the ripple here. And also by proper control, which I'm not going into it in this particular minute, I'm going to discuss it later on. Proper control, you can have a fairly high current coming in, because each one of these inductor is a low inductance inductor, which you can get by because of the interleaving and the total being a low ripple. And by, say, activating all these together, you can get a fairly high IDT. So this is the classical approach that is being used quite a bit. There is, however, a buzz now about the so-called multiphase trans-inductor voltage regulator. Okay, and in this case, the trans means actually a transformer. We see that it is very similar to the multiphase, the classical multiphase, in that we have a number of inductors. Here we have 4 inductors, and here is the input, and here is the output. It's drawn a little bit differently, but in this case we have also a secondary winding on each one of these inductors. So this is actually a coupled inductor, you might say, and then you have a secondary here, and all these secondaries are connected together, and furthermore there is now an inductor here at the end. Okay, and I'm just showing it in a different way, the same thing here. I'm not drawing all of the 4 or n stages, but rather only 2, and of course in between we're going to have more stages. And what we see here again is the inductor. This is the main inductor. This is also the inductor, but as I've said, there are secondary windings on each inductor. Usually it'll be 1-to-1, at least the way it is described recently. So it's a 1-to-1, and here we have an extra inductor loading all these voltages which are actually connected here in series. So in this presentation I'm going to explain the operation of the TLVR in an intuitive way. This is the purpose of this presentation. Although I'm going to show some comparison to the conventional multiphase Buck, I'm not going to do actually a rigorous comparison on the same basis, same magnetics, same control, etc., etc. This is rather a complex issue, and of course I cannot get it into this 20-minute or so presentation. Hopefully I'll do some of it in forthcoming videos. So the first thing to do is to simplify the circuit by modeling using a equivalent circuit, and I'm using here an equivalent circuit for this coupled inductor, and in this equivalent circuit I'm putting the magnetization on one side and then the leakage on the other side. In one of the videos that I referenced, there is a detailed explanation of this transformation, so I highly recommend that you look at it. Anyhow, this is the equivalent model that I'm going to use for each one of these transformers. So if I do that, what I see is that here I have a LM, a inductor on the primary, and on the secondary I have a leakage, okay, and this is now an ideal transformer, okay. So I have an ideal transformer, a leakage. All these leakages are of course connected in series, so in fact they are adding up to this L sub C, which I'm going to put, so it's part of the loading of the secondary by the inductor. So it's LC plus N times this leakage, and then again I have on the primary this inductor. So now I have a transformer here, or a coupled inductor. There is a voltage on the primary, which of course is reflected to the secondary, and all these secondaries now are connected in series, and I'm showing here the secondary side. We have the secondaries all connected together, and then I have the leakages n time, whatever number of stages I have, and if I like, then I can add another L sub C. So this will be this secondary. The primary again is this inductor. This is an ideal transformer. Ideal transformer is defined by having a infinite inductances, so they don't add to the current, but it has a perfect coupling between primary and secondary. The original unit is assumed to have a coupling coefficient, which is of course smaller than 1. Now each primary of these coupled inductors is subject to a pulse coming out of the corresponding half bridge. So we have a pulse coming out, and here I'm showing the primary, and this is the secondary. So on one side we have the pulse coming in, on the other side we have the output voltage. Here it is. So we have a voltage on one side which is V in minus V out, and then we have only V out. Of course I'm neglecting drops here of the transistors. If it's a diode on the diode, it's just a generic operation, generic behavior. So this is what we're going to have at the primary. Volt second here of course is 0 over a period, And this is now reflected to the secondary, and then we have all these secondaries connected in series. Now the pulses are shifted, of course, we'll see it in a minute. So this is one pulse, one half bridge, and then we have the other bridges which are, of course, shifted. And to examine this further, I've built a very simple generic equivalent circuit in which I've replaced the half bridges with just a pulse source. It's a 12-volt pulse here. V in here, it's 12 volt, and the duration, of course, is the on time, and they are shifted. I can change the duty cycle, it's the parameters. I have here the coupled inductors, here, 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 and here. And here is the primary, this is the secondary, and then I have on each primary a resistance, for the wire resistance, and then I have a resistance at the secondary. This is the inductor, which is the extra inductor plus the leakages. This is sort of summing everything up into one inductor. Now this is now representing the load. This is the resistor. This is the capacitor. This is just an option to have a pulse at the output. Let's leave it alone in this minute. And then I have here a zero voltage source used as a sensor. That is, I'm referring to the current through this voltage source. And this represents then the generic converter. So I'm now running it. Here it is. And what I'm seeing here, and this is for a duty cycle of 0.1. So I see the voltages across the secondaries. And here it is. I have the duty cycle is 0.1. The input is 12 volt. So the output is, say, 1.2. So the difference is a little bit less than 11 volt. And this will be like 1.2 volt minus. So here, this is again the voltage across the secondary, and then the other secondary, etc. And these all are, of course, connected in series, and here is the summation of all these. So I have here pulses which are coming from the primary to the secondary and are being summed up to the total voltage of the secondary, which is then fed actually to the load, which is the inductor. This is the L sub C plus the leakages. I'm calling this V sub O. This is the total voltage. Now, obviously, when the duty cycle is 0.1, then there is a void. As you add these up, it's a 0.1, then there's a delay of a 0.25 because of a duty cycle, because we have 4 phases, and therefore the shift is 0.25. So there is a shift here, there's another pulse coming in, okay? Therefore I have this square wave at the summation. Now if the duty cycle is 0.25, I'm sort of filling up, okay, this plus this plus this plus this is sort of filling up, and therefore it should have been like a straight line here, but due to the rise time of each of these, so it's not a perfect square wave. I have these spikes here, but theoretically it should have been like a straight line here, and the value of which should have been 0. Actually it's a 0, but there are these spikes, as I've said, due to the rise and fall time. Now, due to this voltage now, as it is imposed on the inductor, I mean the secondary side inductor, this L sub C plus the leakages, then we're going to have some ripple here. But again, this is the case in which we are sort of filling up the period with these pulses, and consequently the ripple is very, very low. We're talking about milliamp. So this is really very small ripple. So here is again this case of the 0.25. It's sort of a zoomed picture. I have the voltage, total voltage of the secondary, that is all the secondaries connected in series. I have the resulting ripple, And then if the duty cycle is 0.1, as I've said, there is a void, and therefore we're going to get a square wave at the secondary, and the ripple will be much higher, of course. And here I'm showing in this particular case, it's just a numerical example. I'm going to have like something like plus minus 5 amp. Okay, this is really dependent on the system, and it is a result of the fact that summing up all these voltages is not a DC, it's not zero, but rather there is these voids between the pulses, and therefore it becomes a square wave. And depending on the duty cycle, then we're going to have a ripple, depending of course on the size of the inductance that is loading the total voltage here. So now, if I have a duty cycle of 0.25, and this is the total ripple of the secondary, and this ripple now is of course being reflected to the primary. Let's have a look at it. If I have a current at the secondary, due to decoupling, this current will be reflected to the primary. Because it's a coupled inductor, there is an ideal transformer in between, and therefore the current here will be reflected to the primary. Now in the case of a duty cycle of 0.25, due to these spikes, I have some ripple, which is not very big, depending again on the rise and fall time. It's a little different simulation here. And then it is reflected to the primary, which has on its own a triangular waveform. Because this is like a regular buck converter. There is an inductor connected between the midpoint of a half bridge to the output, and consequently the inductor is causing this triangular waveform. Now we have a native ripple at the primary to which I'm adding the secondary, but in this case the secondary is really small, so I really barely see it. However, if the duty cycle is not 0.25 or 0.5 or 0.75, because in all these singular points of a duty cycle we're going to have 0, then if it is not, like it is 0.1, then I'm going to have quite a bit of a ripple, which is now being added to the primary, since it is reflected to the primary, and here is the waveform that I'm expecting now at the primary. Now this is for one phase. I have 4 phases here, which are shifted, and all are summed up, and of course fed to the output. Okay, so this is really what happens. And here is another look using the so-called performance analysis. Now this axis is the duty cycle. Okay, so this is like this is like 0.74 duty cycle. I'm seeing here the RMS values of the ripple. This is the ripple at the secondary, and as we understand now, at the points of 0.25, because it's exactly filling the period. 0.5, 0.75, we're going to have a dip here, almost 0, very little ripple. The ripple here is maximum. This is the secondary side due to the summation of the voltage and the loading of this inductor, L sub C, and the leakage. And this is now the total current that I'm going to see at the primary due to the, first of all, the native ripple due to L sub M, plus the injected or transferred ripple from the secondary to the primary, and this is for the 4 phases. So again, I'm going to see here sort of a dip, because the native ripple of the inductor, when summed up of 4 phases, also has a dip. Like in it, this is like a regular multi-phase interleaved converter, but here we have an additional ripple due to the ripple that is injected from the secondary to the primary. I don't see it. This is not a time domain presentation. This is sort of a summation of the RMS values. So what we have seen here is the RMS of this current here, the secondary, and the RMS of this current, which is now the total of the primary, plus the current which is injected from the secondary to the primary, and this is the I sub total. So here it is. This is this secondary, and this is the primary. So let's see now what happens if I have a step load, as I've considered earlier, in this particular case with the trans-inductor configuration. Okay? So I have a load here, which is changing, like a step in the current. Consequently, I'm going to have a drop in the voltage here, as I've said earlier. This drop is now sensed by the control, and now this control is activating here the PWM, or the pulses coming to these half bridges. Now there are different ways to go here, and I'm assuming now, at this first example, that this change, okay, at this particular instant of this transient, that this change is affecting only one half bridge. Okay, this operational half bridge at that time, or at this time, is affected, and therefore it's now getting an extra high level of a drive here, extra of what is supposed to be. So we have here the load, we have here this extra voltage, the drive here. Now this is of course now reflected to the secondary, because the secondary is now sensing this drop, this change. Okay, so the secondary sees this thing, and therefore there is a change in the current of the secondary due to this change in the voltage here, reflected here, so causing a change in the current. Here is the current changing at the secondary, and then this current is now reflected to the primary, being added to the current of LM, which is also increasing because of the change here. Now notice that the change in the current here of the secondary is reflected to each one of these, and now these are in parallel. So I'm getting n times a change in the primary, I mean the total, because I have in each one of them the change reflected here, and all these are in parallel. So I have then the total change will be the change in the current of the primary. Actually, this should not be n times, this should be just delta I in this particular case, because only this one is changing, I'm sorry. And then n times this change in the secondary, which is here in series, and here it is in parallel in all of these. So there is sort of a, you might say, amplification effect, that the series current here is now reflected as a parallel current, so therefore you're getting a current which is n times larger than the current here for a one-to-one configuration. So now I'm going to simulate this case. However, I'm not going to put in a control because it's going to be complicated to have a fast control, stability, etc., etc. So instead, I'm going just to add a pulse to one of the phases. Okay, so these are running as usual, and then at one instant, this 2.96 millisecond, I'm going to add a pulse which is about 2 microseconds added to here, which is sort of mimicking the case in which you have a change and the control is sensing it, and then it is affecting the drive of this half bridge here. And here is what I'm seeing for this TLVR. Let's have a look first of all at the half bridge. This is the half bridge. This is the added pulse, okay? And this is now reflected to the secondary. Secondary, I'm seeing not only this one, but I'm seeing all the other ones. This is the square wave here. So this change here, this pulse is reflected as a change in the voltage of the secondary. This is the total voltage, all the total voltage. This change is causing a current change in the secondary. This current change is now reflected to all the primaries, and now this is now the total current coming out of all of the inductors or the coupled inductor into the load. Okay, now I'm showing here one pulse, and there is a transient here. This is not the way it's going to be operated in a real system. In a real system, I'm going to capture it somewhere here and to stop, of course, the rise, because I like to have a smooth transition. So this is just for demonstration. This is not the way it's going to work. But what I'm looking at is the IDT. This is the thing that I'm interested in. This is the IDT resulting from a disturbance in the duty cycle or in the PWM signal, you might say, and this is affecting 1/2 bridge. And as you can see, we see a change in the order of, I'd say, 400 to 500 amp, okay, in these 2 microseconds, okay. Here, this is 2 microseconds, so I have a change of 400 or 500 amp. That's quite a, of course, depending on the system. This is a high current system. Now, to be fair, I'm going now to see what happens with the regular classical multiphase. To do this, I'm neutralizing the effect of the secondary. Okay, so it will not affect the primary. And this I'm doing by having here a very large resistor. So if there is a very large resistor here, then the voltage that will be reflected here from the primary to the secondary will generate a very little ripple, and therefore it's like having no secondary. Okay? So this is like mimicking the case of the regular multiphase. And here is what I'm getting. Here I'm getting also quite a bit of a change, but as you can see, it is much smaller. But the difference is not fantastic. I mean, in this case, it's about a factor of 2. Okay, that's what it is. Maybe a little bit more. So there is a change, and I'm getting a DIDT which is certainly faster, but it's not very, very big. Again, don't worry about this tail here. This is not the way it's going to be in a system. In a system, we're going to capture this control, will capture this signal here, and will stop, of course, the extra voltage here so as to smooth out the output. There is another way to do it, I call it, say, nonlinear control, in which when a drop is recognized, then it will affect all the legs. That is, all the legs will be pulled to be high together in order to maximize the DIDT. I am doing it then by adding a voltage source to all of them together, not just to one of them, but to all of them together. Okay? And here it is, and this will be for the classical. Okay, this is the classical multiphase situation. This is not the new TLVR. And here I also have some measurements. This is again the same story. We have this extra pulse. I'm showing it on one leg, but now this extra will be on all the legs because this is a voltage source affecting all sort of the half bridges, you might say. And here I have actually the slope, which is like 267 amp per microsecond. Okay, so 267 amp per microsecond. This is the slope here. This is the IDT that I'm getting in this case. Now I'm comparing it to the response of the TLVR. This is the new design, new topology. And again, I have this pulse coming up. In this case, by the way, it's a 1 microsecond pulse affecting all the phases. This is the secondary. You see how it's reflected to the secondary. This is the current of the secondary. And this is now the total current of the primaries going into the load. And in this case, we have 1,000 amp per microsecond. So here we have 267, and here we have 1,000. So it's a fourfold. It's 4 times faster. Now, clearly, this is for one case, and I'm just comparing the two by assuming that the inductors are the same and operation is the same, and this is unfair, of course. A good comparison has to be on a basis of, say, same magnetics, same cost, same, in other words, it has to have some basis for comparison and not just, taking one and eliminating the secondary and comparing the two. So the point is that no question about this, that the TLVR is indeed giving a faster DIDT. This is clear. The question is, of course, if you compare it on a practical basis to the old classical multiphase converter, on some practical basis, if you are really getting an advantage here. So in this presentation, I've just tried to explain how this TLVR works. There's really no rigorous comparison, so you can't say from what I've presented if it is good or bad or better. It needs much, much more work to be done to really have a fair comparison between the two. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.